Okay, your question is what sets? Yeah, so your question is what sets the DC bias? So let's take this difamp. So it got stuck. Yeah, your question is, I presume, who sets the biases for M1 and M2? Is that correct? Yeah. So let's put these current sources here first. So from whatever we have done till now, what do you think is a good way of biasing M1 and M2? Then we can discuss further. Anybody can answer, not only. Right. So even before saturation, you would like to have them to be turned on, right? So let's start from there. So how would you ensure that M1 and M2 are in saturation, or at least turned on? Should be greater than VGS. Correct. So what you need to apply something at the gate. Yeah, but the source of M1 is the drain of M1. Correct. So it would have a minimum value. Right. Therefore, I need to get my gate voltage above one threshold voltage of that minimum value. Right. At least, right? At least. Right. So that we will see what is that minimum value, but at least we can agree on the fact that you need to apply a DC voltage here. Right. So this DC voltage we were calling a VB, like VB, or you can call it VCM, that is common mode voltage applied between the two terminals. This is one way of doing it. You can put a resistor divider and then also bias. But the question is will it have too much of an effect if this DC voltage varies slightly? In a common source amplifier, it was having a lot of effect, right? Because GM was changing, current was changing, all those things. In this case, will it have too much of an effect? Current won't change because current is determined by that. Right, it's a constant current bias circuit. Yes. So current won't change. Even if so gate voltage changes, source would accommodate for that. Right, exactly. So if both of these gate voltages of M1 and M2 change, the current cannot change, which means the source of M1 and M2 has to move to keep the VGS constant, right? So that's what's going to happen. But what ensures that it is saturated? Okay. So we'll again look into that. But since you asked the question right now, let's see. Let's consider the case with M1, right? So let's do that right now, right? Since this was a second agenda, but since you asked the questions, we can do it right now. So let me call this voltage VB. This voltage is also VB, right? So let's do the minimum one, then we will do the maximum one. Okay. So his question is, how do I ensure that all these transistors are in saturation? I don't have to ensure anything with the diode transistor there because that is a current source driven, always in saturation, no issues. Now, I'm asking you, what is the minimum VB? To keep all transistors in saturation turned on and off. So how will you go about analyzing this? So I'm giving you these options. This is current I0. This is 1:1 mirroring ratio. M1 is equal to M2, M3 equal to M4. So now tell me the steps. I mean, not the steps per se, but tell me your thought process. If I keep reducing VB, what can go wrong?
The drain of M1 is fixed value.
Okay. Why do you think drain of M1 is in fixed value?
Because current will be divided equally in both the branches.
Right.
So M3 has source fixed.
So let's put the current together. This is I naught. So if everything is symmetric and all, this current will be I naught over 2. This current will be I naught over 2. Right?
Three source is fixed.
Yes, source is fixed.
Therefore, its gate would be automatically adjusted to handle that current. And it is also in saturation due to the diode condition.
You are talking about M3.
M3.
Right. So M3, so what will be the gate voltage?
The gate would be such that it should accommodate that.
Right, exactly, right. So gate voltage will be 1 VSG below VDD. Right? So this voltage is equal to VSG. Right? So this VSG is equal to what? VSG for the PMOS for M3 is equal to same, right? One threshold voltage plus overdrive. And what is overdrive? 2 I naught by mu P Cox W over L for M3. Correct? So you see that if I naught is constant and we are talking about same temperature and all, then PSG is not changing. Right? So this voltage becomes this voltage becomes VDD minus VSG. Minus VSG 3 for a current of I naught by 2. Correct? So that is constant. We'll get to the right hand side part later, right? So let's do the left hand side part. That is the left branch. So that is constant. So that is not moving. So if I change VB, if I reduce VB, will that voltage change? It should not, because the current is not changing. Is that obvious to everybody, or that's not obvious? If I change VB, if I move both that, since these two are same voltages, the gates of M1 and M2, if I move them simultaneously, will the current change? Let's say I move them, small amount. Will the current change? It should not change, right? Is it anybody who want, is for anybody, is it not obvious? Then I can elaborate on that. Okay. So if we understand the current doesn't change, which means the voltage at the drain of M1 and M3 is not going to change, right? So now what? Now let's say reduce VB. So what can go wrong? Yes, Arun. Vx, what's going to happen to Vx? Go down or go up?
No.
It will go down. It will go down at what rate essentially? So to the VGS of M1 is again equal to threshold voltage plus, sorry, this was I naught by 2, right? 2 I naught by 2 by mu n Cox W over L of 1, right? So VGS is what? VGS is VB minus Vx, and this is equal to this stuff. And for a fixed temperature, for a fixed current, none of the right hand side terms are changing, right? Threshold voltage is changing, I naught is changing, W by is changing. So VB minus Vx is constant. If I reduce VA, Vx has to reduce. So what is the minimum I can go before something can go wrong? Okay, before that, what can go wrong? Now, if I keep on reducing VB, what can go wrong? M0 is trying to go out of saturation, right? The drain voltage of M0 is reducing. So what is the minimum that Vx can go to? Overdrive of M0, right? Exactly, right? So Vx min is equal to overdrive of M0, which is essentially 2 I naught by mu n Cox W over L of M0, right? So if this is Vx min, then what is VB min? right? So, no, VB min will be this plus the VGS of M1. We're talking about VB is the gate of M1, right? So Vx min plus VGS of M1 for a current of I0 by 2. Right, so this is the minimum allowable voltage to keep M1, M2 on and M0 in saturation. Right? Okay, so there is a fancy term for this. It's called ICMR minus rather. It's called input common mode range negative. We are trying to, VB is obviously the input and it's a common mode voltage because it has been applied to both terminals, both the gates of M1 and M2 simultaneously. And how we are talking about how low can it go? We're talking about the negative side of the swing essentially. So it's called ICMR minus, right? So this is ICMR minus. Okay, so this is the minimum voltage that the common mode at the input can go before causing an issue, essentially, right? So if you are a designer, what you have to sometimes decide what is the minimum voltage, minimum bias voltage that you can give with while keeping all transistors in saturation. So this is ICMR minus. Any questions on this? Okay. So now, again, let's only consider the left-hand side of the branch. So since we have an ICMR minus, then we'll also have an ICMR plus, right? Which essentially will mean how high VB can go. Okay. So now tell me, if I only consider the left side branch, not the right side branch, how high can the VB go? Yeah, exactly, right? Very good. So if I know this voltage, I know that VB can go only one threshold voltage higher than that voltage, right? So ICMR plus will be, if I only consider the left-hand side, again, that is critical. ICMR plus, or let me call it VB max for the time being. VB max will be one threshold voltage plus that voltage, which is VDD minus the overdrive VDD. So this is N, right? VDD minus that VSG. VSG is threshold voltage of the PMOS transistor plus mod overdrive of the PMOS transistor. Okay. So this is if the ICMR, if the maximum VB is set by the left branch, then this will be the this bottom line will be the ICMR plus. Okay. So now the question is whether it is set by the left branch or it is set by the right branch. For that, we need to understand what will be the quiescent V0. Now the question is, do I know what the quiescent V0 is by just looking at this structure? Same as the left side. One argument can be made, it's same as the left side, but it doesn't necessarily have to be. Let's say I ignore channel length modulation. If I ignore channel length modulation, can I definitely say that V0 will be equal to the left, whatever voltage is in the left side branch? It's not necessary, because as long as transistors in all the M2 and M4 are in saturation, then V0 can be anything without affecting currents, right? So we cannot definitely say. But now if we do not neglect channel modulation and everything is perfect, then an argument can be made the left and the right branches, since both the currents are equal, right? So, or rather have to be equal, the only possible solution is both the drain voltages are also equal. Otherwise, there will be an inconsistency if I do the calculation on the PMOS side and the NMOS side, right? So that argument can be made, but that is a very weak argument, because in general, you do not use a differential amplifier in open loop, right? You must have used 741 op amps and other in various experiments. If you keep an op amp in open loop, inevitably it saturates, because you always have some mismatch at the input and so on, and so because of the high gain that you get, the op amp output tends to saturate. So we should not be surprised, because ultimately we wanted an op amp, we wanted a high gain amplifier. What was the reason? The reason was to put it in negative feedback. That was the overarching reason. We were seeking to find a differential amplifier which can give us a stable output when put in negative feedback. That is the crucial part. So before we have to find out what is the quiescent V naught, we need to understand how this differential amplifier has been wrapped around in a negative feedback loop. That will set V naught. Okay. So for example, if we go back to our negative feedback system, so let's say this is our differential amplifier. This is terminal plus and minus, and this is output. And maybe I have a load or something, load capacitance, I don't know, something is there. So which terminal should I connect V naught to ensure that the system is negative feedback? Plus or minus? Plus or minus? Plus. Why plus? How will you go about analyzing whether this is proper negative feedback or not? Yeah, so you somewhere in the loop you give an excitation and see whether the excitation comes back in the same direction or in the opposite direction, right? So let's do that here. So loop is now only this, pretty simple. So loop is only this. So what do you think in this case? What's happening? So if I apply an input, if I apply an excursion here, if this voltage increases, what's going to happen to the output? Yeah. So this guy increases and this is connected, right? So it's a positive feedback. So there are only two options available. If this is not the case, then this must be the case, right? So again, you can go around and check if this if input increases, output decreases, and it's connected. So this is a negative feedback. So what is the equivalent of this in a transistor level configuration? So, but then again, I mean, before proceeding, so let's say this is VB, right? So what do you think V naught quiescent will be? Yeah, tell me. So assuming channel and modulation and all, this is an ideal voltage control voltage source of value, let's say some GM. So what is going to happen? So which equation should I solve to find that out? It can be done in two ways, but let's do the obvious way first. So what is the current that is being driven out? Right. So GM times VB minus V naught. Right. So, and this, if I at DC, I neglect capacitance, this should be equal to, this is current, right? So this should be equal to what? Zero, right? At DC, capacitor is not there. No current can flow inside. Nowhere to go. This is zero. So what is V naught? Then what is the only possible condition for V naught? VB. Right? So this will settle to VB. Right? This should not surprise you, because what is the loop gain of DC? Why? Loop gain. Loop gain means you are breaking the loop and finding out the return ratio. So for loop gain, you break the loop, right? and apply a test voltage at that negative terminal, and you incrementally short the positive terminal. So what will be the current? GM times V test, negative of that, because it's, what is the impedance it's going into at DC? Infinite, right? So what will be the incremental output voltage or the return voltage that it will generate? Don't hesitate, you know the answer. Finite current going into an infinite impedance produces infinite voltage, right? So what is the loop gain at DC then? Infinity. If you have loop gain of infinity at DC, what is the steady state error? 0. So what should we expect those two terminals to be equal? Right? Infinite loop gain. I mean, consider this to be an ideal op-amp. Right? So if this has infinite loop gain, so it should have 0. Basically, those two terminals are virtually shorted. Okay. And this is shorted because the output is connected to the input, or some part of the output is connected to the input, and the loop gain is infinite. Okay. Okay, fine. So if that is the case, now let's go back to our transistor level equivalent. By the way, even before proceeding, if I don't neglect channel length modulation, I will have some resistance. But this GM times this resistance will be high, right? I mean, that's the whole expectation of designing this kind of amplifier. GM times this R out will be high, which means this equation will not settle to 0. You will have some finite current, but that will be small enough. Okay, since that will be small enough, VB minus, the difference between the input terminals will not be exactly 0, but it will be a small value. Expectedly, it will be a small value if you have designed it well. Right? So while you are trying to figure out where the input voltage is going to settle approximately, it's a fair enough assumption to make if you consider both the terminals to be shorted. If you are trying to figure out what is the error voltage, then you cannot assume that to be shorted. But if you are for a zeroth level approximation, you can assume those plus and the minus terminals to be shorted when things are in negative feedback. Okay. For example, if VB is supposed to be 1 volt, and after putting in negative feedback, it's like 0.95 volts. That's fine. You can assume for with zeroth level approximation, I can say that the plus and the minus terminals are approximately at 1 volt. Not too much of a problem. But if I tell you what is the difference in voltage, then you cannot say 0. Then you have to actually find out what is the error voltage. So that's something you should keep in mind.
Sir,
yes.
We were modeling this as an opamp.
Yeah.
But opamp also has property that output impedance.
This is not an opamp, that's why. Right? But loop gain is infinite. Right? So that's the critical difference. This is the voltage control current source put in negative feedback. Okay. Okay, so it's not an op-amp, it's a difamp, kind of. So now, what is the equivalent of, so I have now two terminals, VA and VB, and this is V0. I want the equivalent of whatever you see on the top in the transistor level circuit. So where should I connect V0 to? Either VA or VB. So where should I connect it to ensure that this is a negative feedback? So why not VA?
You can check.
Yeah, check. So Mohan, what do you think? So let's connect V0 to VA. Okay. And now if I increase, let's say anywhere in this loop, I increase this voltage. Incrementally, we are doing incremental analysis. So assume this VA, applied VB is equal to 0. Right? So incrementally. So if this voltage increases, what's going to happen to this current? This is increase or decrease? This will increase. So this current is again mirrored, right? So this current is going into this node voltage. This is increased. The mirrored current is also increasing, right? So into the node voltage V0, the node voltage V0 will increase or decrease? It will increase, right? Current is getting driven into V0, it's going to increase. So naturally, this is positive feedback because that voltage is again getting fed back. So that is not the case. Then obviously only other solution is this. Okay. So now let's see who sets. So approximately V0 will be quiescent wise equal to. So let's say I have applied a battery here of value VCM. So V0 will be approximately what? VCM, right? Set by negative feedback. The loop sets the output voltage, right? So again, now you can also, now let's say I change that VCM on the left hand side. What's going to happen to the right hand side? Let's say I increase VCM on the left hand side. What's going to happen to the right hand side? It is going to increase. If I reduce, it's going to reduce as long as things are in saturation, right? So both the terminals move in unison. So that is why this ICMR spec is also important. It's not just a made up spec just to identify where the biases are. I mean, how high and how low it can go. It's also important because even though you're applying an input at only one terminal, the other terminal is following it, right? Because you have high loop gain. So essentially, even though you are applying input at one terminal, the opamp, the differential amplifier is behaving like it's in common mode, right? Because negative feedback is not allowing it to change the other terminal input. Both of them move up and down in unison. Okay. So we can as well do the analysis in open loop to figure out what is the maximum voltage that can be applied to either of these terminals. Because when you put in negative feedback, that's what is going to happen. Okay. So now, if this is it, in this particular configuration, the one that I showed, right, I'm showing right now, what is the maximum that VCM can go to? So if I consider the left branch, we did the analysis, right? The left branch is being set by, if I cannot cross this voltage by more than one overdrive of VCM, right? What about the right branch now? If I consider the requirement of the right branch, what is the maximum VCM? Will it be same? If I only consider right branch and I increase VCM, who is going to get affected first? M4, right? M4 is going to be affected, not M1, M2. Because M2 is always in saturation, that is in diode connected state, right? So if I increase this, M4 is going to get affected. And how far can I increase this? What is the maximum this voltage can go to? Yeah, what? So let's say this voltage is VB4. So what is the maximum that this drain voltage of M4 can go to? VB4 plus the threshold voltage, right? Because you have a maxima constraint on the PMOS, right? So this voltage max can be, so V0 max can be VB4 plus mod of VTP. I say mod because traditionally it's written as negative threshold voltage. Okay, for a PMOS. So if the difamp is put in this configuration, the ICMR plus will be the minimum of this constraint and the previous constraint, right? So yeah, so on the left hand side, M1 can go into triode. On the right hand side, M4 can go into triode. But the minimum of the voltages of VCM will set the ICMR plus. Okay, so ICMR, this is not obvious in many textbooks where the calculations are done in an open loop fashion, and we say that there is some heuristic that is used, but when you are doing an actual design, the right hand side voltage is set by negative feedback. Now, the one that I showed you is unity gain. If it's not unity gain, then it might not necessarily be that V0 will be exactly equal to VCM, right? It can be something else, right? Because for example, if something is connected between here to there and you have some voltage divider and all, then V0 will not be equal to VB or VCM. Okay, so in that case, you'll have to see what is the maximum and the minimum, right? So ICMR plus or minus can change based on what configurations are, right? So as far as the design perspective is concerned, right? But generally it is understood that it is based on this unity gain configuration. Like most of the data sheet that you check are for this, generally in this configuration when used in open loop. But again, we'll not use op-amps in differential amplifiers in open loop. Okay. Any questions regarding this? Okay, fine. So if there's none on this, so let's move to the next agenda. That is, we have done differential gain, we have done common mode range, we have not done common mode gain for this structure, right? So let's do the common mode gain for this structure. We have done the common mode gain for the resistively loaded differential amplifier, but not for this active load. And let's say this is incrementally R0. And this is, again, everything is biased properly. We are trying to figure out what is the common mode gain. So VICM are the two inputs, let's say. And I can figure out what is the increment. I'm trying to figure out what is the incremental short circuit current. Okay. So now, quickly, can you tell me what will be this voltage approximately? It will be VICM. It will be slightly different from VICM because if I change VICM, some current is going to flow into R0, right? But it will be approximately VICM. Or you can do a half circuit analysis to figure out, you break this R0 into two R0 in parallel, and nothing flows in between, then you can find out what Vx will be. It will be like VICM times GM R0, GM times 2 R0 by 1 plus 2 GM R0. So assuming GM times R0 is much greater than 1, this will be approximately VICM with some steady state error. So this is VICM. What is this current that is flowing through R0? And that current is getting divided equally on both sides. So this current will be VICM by R0, 2 R0. This current will be VICM by 2 R0. Fine. So now what's happening on the mirror side? So the current through M3 is how much? So what will be the current through M4? So what flows into the short? Is 0, right? Because whatever current is coming in is also going out. Nothing is flowing into the short. Right? So what if no current is flowing into the short, ISC is equal to 0. Right? So what is the equivalent? Now, I mean, this is only ISC, but in the Norton equivalent, the ISC will get multiplied by the output resistance. Output resistance, we know it's a R04 parallel R02. So, but what will be what is the gain of this configuration? 0. Right? Right? Make sense? So it was not 0 in the earlier configuration, remember? Because there was no current mirroring effect there. Right? When the resistive load was there was no current mirroring effect. So only the bottom part of the current was there. The bottom part of the current was flowing into the short. It was developing a voltage in the Norton equivalent. But in this case, the top part of the current cancels out the bottom part in the common mode sense. In the differential sense, they were adding up. In the common mode sense, they are cancelling. Okay, so you are getting 0. So now whenever you get 0 or infinity, and you are trying to figure out whether it's actually 0 or infinity or not, you need to be suspicious and see what did I neglect. Right? Because you cannot neglect anything with respect to 0. Okay? So now we have neglected multiple things. So let's backtrack and see if neglecting channel modulation of M3 and M4 has made an effect or not. Okay. So what am I saying? I'm saying is that whether the mirroring has been affected because I have neglected channel length modulation of M3 and M4. Okay. So on the M3 and M4 side, if I impose channel length modulation on the M4 side, what should I have? I should have a R04, right? On the M3 side, I should have R03, right? So now, if I neglect the channel length modulation, what was the impedance looking up? Right. If we neglect it, it would have been 1 over GM3. If we don't neglect it, it will be R03 parallel 1 over GM3, right? So, or in other words, its conductance is G03 plus GM3, correct? So what will be this voltage? What will be the voltage at the gate of M3? If I don't neglect R03, it will be this current minus, obviously, because I'm pulling current out, VICM by 2 R0 by GM3 plus G03, right? Okay. So on the right hand side, what will be the current through? Yes. Okay. So let's say so is it clear that the conductor is looking into that node is equal to CM3 plus G03? So the current is VICM by 2 R0. So the voltage will be current divided by conductance. That's all I'm doing. Right? Negative of that because current is being pulled out. Okay. So what will be the current through M4? Then it will be GM of M4 times the gate voltage. Right? So this voltage is VG4. So this current will be VG4 times GM4, right? So this will be GM4 times VG4. Going upwards. Now what is VG4? The one that we just derived on the left hand side, right? And that is negative, which means flowing downwards, the current will be flowing downwards. This current will be GM4 times this VICM by 2 R0 by GM4 plus G04, right? So what about this R04? Will any current flow through R04? What do you think? Will any current flow through R04? No, that is shorted out, right? Incrementally shorted, that nothing will flow. So this goes off. So now you see there is a difference in current that is flowing into the node and that is getting dragged out. Right? What is getting dragged out? VICM by 2 R0. What is flowing in is this. Some fraction of that. It's close to 1, but still there is a difference. So what is the difference? So then what will be the ISC? ISC will be the difference of the one that is getting dragged out and one that is getting pushed in, right? So so this is essentially VICM by 2 R0, which I can take within brackets. GM4 by GM4 plus G04 minus 1, right? So which is VICM by 2 R0, negative of that, times G04 by GM4 by G04. Okay. So this is now in the bottom term in the denominator you can neglect G04 because GM4 is generally more than G04. So this becomes okay. So this this is the short circuit current. This times the output impedance will be the output, not an equivalent of output voltage, and that is essentially the parallel combination of M4 and M2, the resistance equivalent to the parallel combination of M4 and M2. You multiply this term with the output resistance, and you get the common mode output voltage, and then you essentially get the common mode output gain. Okay, make sense? So now one might argue that why? This is done by only neglecting the current that is getting mirrored. I can also do the analysis by neglecting the current, by not neglecting the current that is flowing here and there, because some part of the current goes here, some part of the current can go. Sorry, we are not being equivalent, right? So this is not the problem. We have not neglected the channel modulation of M1 and M2. So if you don't neglect the channel modulation of M1 and M2, you will get some another correction factor. Yeah, granted you will get, but you will not make too much of a difference, because ultimately whatever you will go here, so that guy is getting mirrored, and the mirroring is imperfect. So there will be some additional term, there will be some additional factor that with which this term will get modified, but that's not significant. The significant part is, if we neglected channel modulation everywhere, we would have gotten an output current of 0, but with respect to 0, whenever you get 0 or infinity, you have to be slightly suspicious. Right? So the initial correction factor is much more important than the other correction factors that can come in, because already you have got some finite output voltage. Okay. Any questions regarding this? Yes, no. Okay, fine. So this differential amplifier structure works fairly well if you are looking for a gain of, let's say, 30 dB, 40 dB, and similar to that I gave in the project. But this differential amplifier stuff works well if the load is capacitive. If the load is resistive, then you have a problem, because I'll show with respect to only the GM. So this is connected like this. Let's say we have a load of some RL. Biasing is not a problem. Let's say we have biased it properly and all. Right. So, and if I try to find out the loop gain, what will I do? I will short this one, apply a test voltage, and find out the return voltage. And this will be minus GM times RL times V test. So the loop gain is minus GM times RL. Sorry, loop gain is GM times RL. Right? So you see that if RL were not there, you see that it's directly affecting your loop gain. That's the problem. Right? So if RL is substantially low, right? If RL is of the order of 1 over GM, then your loop gain goes for a toss. Right? So for example, GM is, let's say, 1 millisiemens and RL is also 1 K. You are trying to drive a 1 kilo ohm load, then your loop gain is 1. It means not a very good opamp, not a very good difamp at all. Right? So what do you do in such configurations? If RL is, let's say, 100K, then it's fine. GMRL is 100. You have enough loop gain. You'll probably have less steady state error. It's all good. But the moment RL starts to load the GM, then you have a problem, right? So then what do you do? So then we generally do whatever we had done before when we were doing common source amplifier. With loading problem came. So how did we solve? If you recall, we put another stage after the first stage. The second stage was driving RL, and the first stage was not driving RL. So first stage was giving whatever gain it was giving, almost like a ideal load, right? Which was not driving any quiescent current, we were not driving any incremental current into the RL. And the second stage was trying to give you some gain. Even if second stage gives a gain of 1, you are not losing the gain of the first stage. Right? So, what I'm essentially saying is, if you have to do this, what you can essentially say is, if one stage is not enough, I'll put another stage. and make this drive RL. Okay. And let's say this has some output impedance of R0, which is a internal, which is equivalent to R0 2 parallel R0 4 for this opamp, for this difamp, right? So this is, let's say, R0 2 parallel R0 4. And this GM equivalent is GM1 with respect to differential amplifier. Now, if RL is of the order of GM, you can say I can use two of these differential amplifiers. The second one is probably giving me a gain of 1. The first one is giving me sufficient gain. The loop gain hasn't really degraded, right? So if one stage is not enough, you put two stages just to isolate the second, stage, isolate the final load from GM. Make sense? If you recall, we had done this with the common source amplifier long back, right? Probably lecture 10, 11 or something like that. Okay, so now the question is, how do I do this? Should I put another differential amplifier, or is there a easy way to, or a smart way to go about doing this? Okay, that's the question that I'm asking. Now, you see that, does the second stage need to have, I mean, the first stage, for example, the first stage has two nodes which are accessible. Because in one node we are applying the input, other node was the negative feedback was coming, right? So we wanted identical loading on both the plus and the minus terminals at the input stage. So we needed two stages, right? But is it necessary for the second stage to have also two identical inputs, I mean, equal impedance on the plus and the minus terminals? Not necessary, because incrementally I'm anyway grounding. Correct? So, and moreover, let's say I want to put this in negative feedback. Where should I connect this? Should I connect this to the plus terminal of the first stage or the negative terminal of the first stage? Negative, right? And if I flip these, then should I connect it to the plus terminal or the negative terminal? Plus terminal, right? So if under closed loop condition, input will go, feedback will go there and input will come here. Okay, so let's stick to this. Let's stick to this configuration for the time being. So now you see that this stage need not be another differential amplifier then, because the requirement of having two identical input stages has gone away. The plus and the minus terminals did not have infinite impedance, infinite DC impedance. Okay, so can you suggest an option of implementing this second stage GM with using a transistor equivalent? Common source amplifier, not common gain, common source amplifier. Okay, so we can do that. We can essentially say so VB. So I'm showing in the open loop case, all right? VB. Now this is the output of the first stage, and here I have some RL. So I have to put a common source amplifier between the output of the first stage and the output of the second stage. So here I have to put something. So now we have two options of common source amplifier: PMOS based common source amplifier and an NMOS based common source amplifier, right? So what will determine whether I should put a PMOS based common source amplifier or an NMOS based common source amplifier? So if, let's say I use a NMOS based common source amplifier, which means I'll have something like, I mean, let's start off with the resistive load, then we can also do the current meter load. So this will go here, right? And there's probably a AC coupled output that's allowed if the spec says so. So now, do you see? I mean, in principle, incrementally, PMOS based common source amplifier and a NMOS based common source amplifier, NMOS based common source amplifier are identical. So definitely, whether the choice has to be a PMOS or an NMOS is not dependent on the incremental model. it has to be dependent on the quiescent states. Okay. So now tell me, do you see an issue, possible issue, if I use a common source amplifier, a NMOS based common source amplifier?
Might not have access to that.
Might not have access to
That terminal.
which terminal?
That capacitor left terminal.
No, this is the output side, right? I mean, this is the output of the differential amplifier. So you have access to this. That's not an issue. So quiescent wise, do you see an issue? So let me give you a hint. Approximately, so let's put some numbers. If I put a number, then it will probably make more sense. So let's say this is 2 volt. Yeah, I think you are on the right track. Tell me. Yeah, that's the essential problem, right? So let's say this is 2 volt, and let's say your threshold voltage is of the order of 500 millivolt. I mean, that's what you generally get, not 1 volt. And let's say overdrive is 100 millivolt, 200 millivolt of that order, right? So if that is 2 volt, threshold voltage 500 millivolt, overdrive of 100 millivolt. So essentially, this voltage becomes 2 volt minus 0.5 minus 0.1. That is 1.4 volt. Right? So, and let's say VB, I mean, you keep a overdrive of 100 millivolt here, and again, a threshold voltage of 500 plus overdrive of 100, that is 600 millivolt there. So you have 700 millivolt of VB. So this is approximately 700 millivolt. Okay. So what is the range of V01 in which V01 can operate? Maxima, minima. This is ICMR equivalent, right? So I'm talking about a threshold voltage. Let's say VTHN is equal to mod of VTHP is equal to 0.5 volt and overdrive of 100 millivolt. So what is the maximum of V01? 1.4 plus 0.5, right? So it can maximum go to, so this can go to 1.9 volt on the higher side. On the lower side, how much can it go to? 700 millivolt minus threshold voltage, right? 200 millivolt. It can go to 200 millivolt. Right? If put in, I mean, this can go to VB minus threshold voltage, right? So there's a minimum it can go to. But you have an issue. If when you put it in negative feedback, this voltage will track this voltage. Correct? But can VB on the both sides can go to 200 millivolt? I mean, sorry. I mean, I made a mistake. So okay, so let me backtrack. Let me backtrack and say that I mean the range of this is 1.9 to 200 millivolt. Okay. So now let's say your application is such that it demands I mean it demands a biasing at the output stage, right? Which demands this voltage to be of the order of 1 volt or so. Right? I didn't tell you why, but let's say you okay, let me again backtrack and say that let's say for some requirement you want this voltage, the output of V01 to be close to VDD, right? Maybe close to 1.9 volt, maybe 1.5 volt, 1.6 volt. Then do you think this output state is a good idea? Because the reason I'm asking is, let's say for some reason you want this voltage to be 1.5 volt. Output stage can have a problem because now essentially you are having a huge amount of overdrive on top of in this output stage. Now if you have 1.5 volt here, what is the range of voltage that V0 can go? What is the minimum that V0 can go? 1 volt, right? The V0 can go at minimum 1 volt. Anything below 1 volt, the output stage causes problem, right? So then you see that you are losing half the power supply just because you have chosen an NMOS at the output stage, right? In terms of the allowable voltage swing. But now if I choose a PMOS at the output stage, right? What's going to happen? And let's say the requirement is still the same. This voltage is of the order of 1.4 volt. What is the maximum this output voltage can go to? 1.9. Is there a constraint on the minima? Can this final output go as low as possible without affecting, let's say, M5? It can go, right? So it's a flipped equivalent of NMOS. In NMOS, the drain voltage can go as high as possible without affecting the saturation condition. In the PMOS, the drain voltage can go as low as possible without affecting the saturation condition. So
you mean that current will go to this, that M5 current will go zero if we will not.
No, that depends on the quiescent stage, right? I'm saying that if the signal swings, if the output signal swings, the incremental current can go through the resistance, right? So this, if the output swings and this voltage is going low, which means that you are dragging less current, which means there is an incremental current flowing in that direction, right? So we are trying to figure out whether the output has a range to swing. So under this quiescent condition, do you believe the PMOS is the better way, second stage, or NMOS is the second better way? PMOS seems to be better, right? So that's why traditionally, in most cases, and another good thing about this using PMOS is both this M2, M3, M4. So M3 is approximately how. So if you bias your circuits in such a way that the voltages on both arms of the difamp are approximately similar, then the arguments of symmetry also holds much better than if the voltages of the both arms of the difamp are not identical or not symmetrical, right? So this is a very heuristic way of explaining. But when put, I mean, this is slightly advanced concept, but I'll just state it. I'll not go deep into this. So you can, an argument can be made is when you put things in negative feedback, if the two arms of the first case difamps are not identical, then in order to make the output track the input, this voltage has to move, right? And this voltage has to move, which means this voltage cannot move as is. The input has to split. If the input doesn't split, the output voltage cannot move, which means that when put in negative feedback, under the condition that under quiescent state, these two voltages are not tracking each other, you will have an input offset. Right? We'll talk about this in E613 in the next class, but I'm just throwing out an idea that it's always better to select an architecture when using difamp where both the output terminals have similar quiescent voltages. Okay. So if that is true, then obviously in this particular case, using a second stage PMOS common source stage is a better idea than a NMOS common source. Okay, so that's why in most cases you will see that in such circuits, the second stage is often an PMOS common source amplifier. Okay. Now, two stage, you are putting in negative feedback. What can go wrong? Yeah, multiple poles, right? So you'll have obviously this guy has a pole because even if I neglect the drain, even if I neglect the drain capacitances of M1, M2, M3, M4, so I'm seeing a CGS capacitance of M5, right? Since we are seeing a CGS capacitance of M5, you are going to have a pole because of the time constant associated with CGS. And regardless of whatever you do, output will also have a capacitance, right? So you'll have two poles. When you have two poles, put in negative feedback, you have a problem, but we have done this in detail. So how to stabilize this? Easiest way to stabilize without compromising loop gain? First, you have to split the poles, right? Because if the output pole and the input pole are of a similar order, you are going to have very poor phase margin, right? So you have to split poles. So how do you split poles? Miller, right? Only one way we know as of now, other than putting a very large capacitance at a node, right? That is obviously one way to put. You can say that I'll put some infinite capacitance in one node, everything is stable, right? So, but that will be also infinitely slow. You don't have too much of loop gain if you have put a very large capacitance. So the fix is put a Miller capacitor, and if you put a Miller capacitor, the poles will split. How will you split by? Now this is exactly same as the analysis of common source amplifiers, multiple common source amplifiers put in a loop, right? So you might get intimidated looking at this structure. So it's always advisable to use block diagrams in such cases. So what is the block diagram of the first stage? This will be some GM1, and this GM1 is essentially GM of the first stage, GM of M1 transistor, right? You have an output resistance, which is R02 parallel R04. Now you have a second stage. So by the way, if I am using the second stage to be a common source amplifier, is this the right symbol, or this will be the right symbol? Which one? The black or the pink or magenta? What I'm saying is this second stage is a common source amplifier. So is this symbol, this terminal negative is the correct one, or the positive is the correct one? Black one, right? Yeah. So this has to be that. It's a common source state. So this is some output resistance RL. You also load it with R04. There is some CL. Here you have a capacitance C1. This C1 is equal to approximately CGS of M5, right? So this is the CGS of M5. I mean, granted there are more capacitances, but generally the gate to source capacitance dominates. So you can use that approximation. And now we'll be putting this in negative feedback. So essentially this guy will go and connect here. Okay. So, but for calculating loop gain and stability, you short this. This is V test. This is V return, right? So, and you see you have two poles. You will have problem. One of the poles is at 1 over C1 times R out R0 to parallel R04. The other pole will be 1 over CL times RL. They might be close to each other. When you put in negative feedback, you have a problem. The solution is put a Miller capacitance. So it will split the poles, right? And there is a hope that we'll be able to get the requisite phase margin. Okay, makes sense? Any questions? So this is the classical two-stage Miller compensated op-amp. It's called an op-amp, by the way. One of the reasons it's called this has an output impedance which is really high. It's not a zero impedance case, right? And it will be even more relevant because now in this case, I used a resistance. You need not use a resistance. You can use a current source, right? I can use a current source here, right? So, and the current source is nothing but another transistor. So this is also a transistor. And there is probably a master current source. And let's say this is 1:1, and this is connected, and this is maybe 1:n. Depending upon how much current you want on the right-hand side branch. But the key thing is that the second stage is still a current source. The bottom guy is still a current source. Okay. So the output impedance of this open loop state is still high. Okay. But then is this an op-amp? Then traditionally it should not be called an op-amp because an op-amp, the output impedance is close to zero, as low as possible. So what configuration do you know that can give me a low output impedance? Feedback does, but let's say not in feedback, I'll come to feedback. A common drain stage. Common drain, you are taking the output from the source of the transistor. It's a buffer, right? Exactly, it's a buffer, right? So essentially what I'm saying is, if this is the second stage, so this is biased with some constant, I mean, some other stage, this is V01. So what you can generally do, use a buffer, and the output impedance is of the order of 1 over GM. Let's say this is M8, 1 over GM8. Okay. So this used to be a very popular topology of using a GM at the output, using a common drain amplifier at the output stage, even like 10 years back or 15 years back. But this is no longer a very popular topology. One of the reasons is, the drain voltage of M8 can go at max where the maximum of the drain voltage of M6 can go, right? So they are connected. Sorry, gate voltage of M8 and drain voltage of M6 are connected. So this is, let's say, 2 volt. This can go at max to, we saw, 1.9 volt if we assume 100 millivolts of overdrive. Okay. Now, which essentially means that V0 max will be what? Right. So 1.9 minus VGS of M8, which is again of the order of 600 millivolt. So this V0 max becomes 1.3 volt. This is the maximum allowed can go. So if you are using a 2 volt supply, you are losing 700 millivolt just for biasing. And 2 volt supply is also kind of high. In modern technology, we use 1 volt supply, but threshold voltages haven't scaled as much. Threshold voltage is probably 300 or 400 millivolt. So if you use this, you essentially lose more than half the supply just for biasing. So we say that we get rid of this third stage, which is the buffer stage, and still use it as an op-amp. Why? Because ultimately we'll be putting everything in negative feedback. And when we put everything in negative feedback, the output impedance anyway goes down. Right? So ultimately what is happening? So so this is what is happening, right? So if I draw it in this format, you'll be able to understand better. So let's say you have something like this. What is the output impedance? This is M8. What is the output impedance? 1 over GM8. Okay, so this is 1 over GM8. So let's say I put gain stage of A. This is plus. Okay, so let's say this is, let me make it explicit. This plus minus gain stage of A. So what is the output impedance now? By the way, we have a loop. Is the loop in negative feedback? So what happens if I increase this? This voltage increases, so this voltage increases. Right? So loop is a negative feedback. So what is the output impedance? Calculate and tell me. That's the ideal gain of it, voltage gain of it. It's still the same, is it? On the left hand side structure. How did you find out? You apply a test voltage, V test. What will be the voltage here? So what will be the current? Gm into V test into A, right? So what is the output impedance? 1 by Gm into A, right? So the output impedance goes down by a factor of the gain, right? 1 over A times Gm. Okay, so let me redraw this structure. Let me redraw the structure in this way. Same, right? Essentially redo. So instead of A, I'll put Gm. And it has an output impedance R0, which is R0 2 parallel R0 4. It's incrementally grounded. So what will be the output impedance now? GM8. This is GM1. What is A in this case? Equivalent to A? GM1 times R0. So the output impedance goes to GM1 times R0 1 over GM8. And what is this structure? This is in an open loop sense. If I break this loop, this is a two-stage opamp. Right? So you can put the output, you can see that output impedance naturally goes down by a huge factor, right? When you put things in negative feedback. So the necessity of putting an output stage, which has by default a loop, which by default has a small output resistance, is not as much. If you can, it's better. 741 op-amp, for example, has an output stage which is a common collector stage, but 741 op-amp has like plus 12 volt, minus 12 volt to work with, right? So in that case, you can afford to lose some headroom without causing too much of issues. But when you are operating with supply voltage of 1 volt, sub 1 volt, maybe 1.5 volt also, you'll probably not be having that large. Okay, fine. Okay. So we'll stop here and we'll wrap up the course on Monday. Right. So there are few of the simple architectures we didn't cover. One of the reasons we didn't cover the few of the simple architectures is because I wanted to cover op-amp first because there was a project. So I'll cover some of the other stuff which has not yet been done deeply in the final lecture. Okay, we'll stop.